Hello everyone. Here we will see the version representation theorem. Let X be an arbitrary set of data set or instance space, and H is the hypothesis space derived with Boolean valued functions over the given data set X. So here C of X will be either 0 or 1 because it is a Boolean valued hypothesis. So which is again arbitrary target concept defined over the instance space X, and dbn data set arbitrary set of examples. Here all the x of training samples x with respect to c of x is given, and we have to make version space with respect to given hypothesis space and respect to data set. Whichever hypothesis is consistent, that may be a specific boundary hypothesis or general boundary hypothesis, which is given from based upon the condition, general hypothesis more general than given hypothesis more general than specific hypothesis. So based upon this criteria we will get any hypothesis which is belong to the hypothesis space capital H. Here we have to prove that every hypothesis H satisfying the right hand side, this is the right hand side of the above expression, is in the version space H comma D. So whichever hypothesis we are taking based upon this criteria, that will be added into the version space. And the second one is every member of version space H comma D satisfies the right hand side condition. So we will see one by one here. First condition is every hypothesis satisfying the right hand side of the given expression vs version space h comma d. So from this g is an set of general hypothesis in the general boundary. S is the specific hypothesis which is available in the specific boundary, and H is an random hypothesis from the hypothesis space capital H which is given. So here the condition is the general hypothesis is more general than selected hypothesis, random hypothesis more general than specific hypothesis in the specific boundary. As per the definition here, we can say yes must satisfy all the positive examples D. So we are taking yes is satisfying all the positive examples given in the data set D. Alright, that means h of xi equal to c of xi. So which is considered as a consistent with respect to this one. So based upon this one we can say considered hypothesis H is more general than the hypothesis which is taken from the specific boundary, which is satisfying all the positive examples in the given data set D. That means here we are taking the hypothesis this is satisfying this condition. And similarly when you are taking the negative samples, here G is not at all satisfying the negative samples. That means H of xi equal to no, and also C of xi is also no. So that is the meaning here, right? When it is not satisfying any example D, then we can say general hypothesis is more general than the H hypothesis, right, which is the random hypothesis selected. And here if it is not satisfied G for the negative samples, then we can say H also cannot satisfy the negative samples. So both not satisfying the negative samples. So which is also no, which is also no. That is the thing, right? Then H is satisfied by all the positive samples and it is not satisfying the negative samples. Then we can say H is consistent. So if it is consistent, we can add that random hypothesis into the version space with respect to given hypothesis space H and data set D. Like that, here we can prove this in the vice versa. Here, if you prove that version space the selected hypothesis H is not satisfying the given condition, then we can say that given random hypothesis is inconsistent. That means if C of xi is some value and h of xi is some value, if both are not equal, then we can say that is inconsistent. So this is the way to prove that any random hypothesis is consistent or inconsistent with respect to the version space representation theorem. Thanks for watching.